Welcome to this next lecture in our Python series. In this session, we're going to take a look at the use of data types and data structures. We'll also have a look at some methods, some functions that we can use to perform typical operations, such as assigning data to a collection, as well as removing it from a collection, finding things within that collection of data, and other such operations that are typical with data structures and algorithms. So we're going to have a look at some Python-specific structures. They're also known as types in Python too. And of course, these concepts will extrapolate to other languages. So we'll explore some differences and some similarities between the other major languages as we go. So we start off just generally an overview of what a data structure is, how it differs to a variable and objects as well that we've also seen. And we'll have a look at some common types, some entry-level data structures such as the array of elements. We'll also have a look at strings. We'll do more on that. We've explored strings in Python, but we'll have a look at how that sits and how that relates to the array, and also the list and how lists are interpreted in Python. Have a look at tuples, the immutable version of lists, it's known as constants. We'll have a look at sets of data and finish up with dictionaries, key and value pairs. Okay, so that's what's on the menu for today. So let's start with generally an overview of this concept of a data structure. So it's a fascinating concept. Indeed, there are whole courses and modules dedicated to this area. Let's start with a simple distinction between a variable and a data structure. So a variable, as we know, would store one value, one item of data at one time. So if I had a simple integer variable, I'd only be able to store one number at one time. So I could assign a value to that storage area. Remember, this is allocated in memory, typically temporary memory, usually, unless you're going to be storing things on the hard drive. But that is obviously different to our variable, which is a local storage area, typically on the RAM. And we assign one value, and that's stored at a memory location. We can access that via the variable name. We don't have to remember the exact location, the hexadecimal address, which is helpful. It's more meaningful for us to refer to this value by the name of the variable we give it. And then we can retrieve that value. We can also overwrite that value later. We can reassign the value, but importantly, we only store one value at one time. Okay. We can also bundle up these variables, these single storage areas, into, we can define them in a class structure. So within an object created of that class, instantiated of that class, we can assign, again, a single value to the variables, the class structure that is defined. So we might have multiple variables that bundle up as part of an object, but we can only store one value to each. Okay, so we're taking that concept a little bit further. And data structures, again, is another level in which we have the ability to store a collection of single values. So we actually have a number of variable spaces, let's say, within a collection. And we have fixed size structures, we have flexible size structures which can expand and contract. Indeed, we're going to see that in Python with a list. We can just keep adding to it, and we can also keep removing from it. Whereas an array typically is fixed. We allocate how much memory that we require at the start, and then we can assign data to individual elements up until the number that we specify. Okay, so that's the key distinction. Variables will generally store one value at one time, whereas data structures can store a collection of values. And however many, it depends on how many we specify and how many we add, of course, to it. So it allows us to group data into a single, let's say, a single entity. We can, rather than having hundreds of individually named variables, let's say we wanted to store 100 values, rather than having variable 1 through to 99, or variable 0 through to 99, where we have it does store it in variable 82 or 83, we can have one, let's say, entity, such as a collection of marks, a collection of person objects, and we can allocate individual elements. So it'll actually be, in the case of an array or a list, it will be access or loop through this collection to see all the values, or if we want one in particular, we can say, well, hey, get me or find me the location, if I don't know it, of this particular criteria I'm looking for. Or if I know exactly where it is in the structure, I can indicate the index. I've got, it's an index structure. If it isn't, let's actually distinguish between index structures and non-index structures before we get into that. So an index structure is where each element of the collection is allocated an index. This is typically an integer value, a digit. With hash tables, with dictionaries, this can also be. This can start as a string and then be converted to digits via the ASCII system. But typically it has a way of looking up a particular element within the series, within the collection. If we know exactly where it's positioned in the array, we can go straight to it. Otherwise known as the concept of random access. That's basically RAM built on that concept. We don't have to start at the beginning and then go through each element to find the one we need. That's a non-index structure. We'd have to do that in that case, like a linked list, where we start literally with one reference point, and if it's not that one, we then have to go to the next one, and then to the next one, to the next one, like a stream of data. We would have to find it that way. We don't, if it's not indexed, there's no other way of getting to it. We would have to go, we just iterate through the structure or take it as it comes. But with an index structure, we can go straight to it if we know its location. And if we don't, if it's still indexed, we could probably look it up. We'd probably find it. Okay, that's the concept of searching and finding via that. So there's a key distinction between index structures and non-index structures. Like I say, index, we've got a value, a position in this collection. If it's not indexed, if it's sequential, we would have to follow through in that sequence. However, that is dictated, whether that's by memory references. Typically it's memory references, and they store pointers to the next one, and the next one, and the next one. That's what gives the concept of a linked list, okay, or a stream of data that is coming into our application from keyboard or from some text file or from some other source. It's going to come in the order that it's prescribed. Okay, so hopefully that gives us a little bit of an overview of this world, this concept of data structures and how to manage data. Obviously, data is an essential area of our digital sphere. So there's so much more to explore about it, but we're going to make a start today. Just to introduce the idea. As I say, it's a concept of much research, and obviously the amount of data that we produce in modern times, and foresight's only that we're going to continue to produce more data. Efficiency becomes an important topic of interest that we need to be aware of. How do we optimize for performance? Again, there's more we could talk about with this, such as big O notation. We can look at the different algorithmic complexity, how much runtime that it's going to take to be able to find and sort and search and insert data into these different structures. We won't cover that in this lecture, but that would be the natural follow-on from this. Indeed, pathfinding algorithms, computer vision, that's where we're getting into neural networks and AI from there. But we're going to start with just performing typical operations of setting up basic collection of values for a simple program so that we can insert data into this structure. We can remove things from it or delete it, pop it from the structure. There's lots of different terms we could use, as well as being able to search and sort too. Okay, so hopefully that sets up this field of inquiry, and let's have a look at some concrete examples now that we've covered that introduction. So let's start with the array. Some of you may have heard of an array before, and let's just remind you of what it is. So it is an example of an indexed structure. The items in this collection are generally referred to as elements, elements within an array. Okay. And in most cases, we have to define how many elements we require when we declare the array. In most strongly typed languages, we're required to specify the size because at the back end it's going to multiply and we also have to specify the type as well, generally in a strongly typed language. So if we require an array of 10 elements and we're dealing with 32-bit integers, we specify we want to store 32-bit integers. Well, obviously, the compiler is going to have to multiply 32 bits by 10, if you want 10 of them, to be able to work out how much memory to allocate for these 10 spaces, these 10 elements that we could fill up with data. So it would require the size to be able to allocate the memory, is what I'm trying to say. Okay, and we've got an index as well. So we would use the square brackets typically, what's known as the subscript operator in C languages. And once we've set up this array, allocated the amount of space we require, we can then get to a particular element. They're typically 0 indexed, so we start at 0, that's the first item in the array, and then it goes up to size -1. Okay, so as says indexed random access, we can get to the middle of the list if we need to. We don't have to go through all the others before it to get to it. We go straight to the one we need. Okay, so that's quite important when we think about performance. Okay, and indeed later. So let's just have a look at what that means. Okay, so here on the right-hand side of this slide, you'll see that we have a strongly typed declaration of an array. We can tell it's array because we've got square brackets. Okay, we don't actually have to do this in Python, but in other C languages and Java, for example, we would have to declare the type int, let's assume 32 bits, 4 bytes, and square brackets to distinguish it from a normal variable. Remember we said right at the start that if it was just int, it would have only store one value, but here we're saying we want to store a collection of values. So marks is our array name, and then we use the keyword new in C and Java syntax that just allocates memory dynamically on a different store of data, the heap, okay, rather than the stack. And we then specify how many integers we require. In this case, 8. So that's going to be 8 times 32 bits to allocate the total number of memory. And then that gives us 8 individual storage locations from 0 to 7 that we could enter a value in. And of course, remember, typical rules like variables, we can only store one value per element. We can't store multiple values in one element of the array. We have to space them out into individual elements. Okay, but each element has its unique identity, let's say. It's got its unique storage area. We can get to a particular element via the index, so it doesn't get confused with the others. Okay. So that is obviously a bit more meaningful than having lots of individual variables, each with a different number at the end. It's going to be quite unruly, take up a lot of space in code. It's far easier just to specify one line of code and indicate we need so many of these individual storage locations rather than 100 individual variables. Okay, so there we go. That's a simple distinction there for the array. Let's move on and have a look for what that means for our string. Okay, and again, in most languages, same in Python, the string is treated as an array of characters. So in Python, we don't have a dedicated character type. We just have str in Python. But in C languages, Java, many other languages, we have a distinction between a string, which is an array of characters, and then just an individual character type, which stores one character. You can't store multiple letters, digits, and symbols. You can only store one at a time. Okay, and obviously it has an ASCII value as well. So str in Python, string, means that we have a string object and it's treated as an array. It's an indexed structure. So here we have an example. On the left-hand side, I've got a variable declaration in Python. I didn't have a type, don't need to worry about that in Python, okay? So we just have name, variable name, equals, and then my name, N-I-C-K, and those are, we store one letter, one character in each element of this string array. So it starts at 0, 0 indexed, so that would be capital N as a single character, and then the next element, which is element number 1, which is actually the second in chronological order, the second element, but the one-th position is the second character, which is lowercase I, and then C, and then K. Okay, so we go from 0 all the way through to size minus 1, which is 3 in this case, 4 characters. Size minus 1 gives us 3, starting at 0. Okay, so I could then get to individual elements, individual characters of this string. Okay, there's one more thing to say just before we move on, which is that a string object is treated as an immutable array. So immutable means that it doesn't change. We're going to see this when we get to tuples. A list is generally mutable, and in a post-COVID world, mutations of the virus means it changes. So that's a reference I refer to because it's one that's etched into our memories. So immutable means it doesn't change. We get no variations of this, no variants. Okay, so it doesn't change. It's static, it's constant. Okay, it doesn't change. So once we declare it, we can't change it, which you're probably thinking, hang on a minute, I can usually redefine strings if I need to. I can add things to them, I can reassign values to them. And yes, that is correct. What it actually does though, in the back end, actually sets up a whole new string object, a whole new string array, and points to that one instead of the original one. Okay, so it's a slight nuance there. We don't see any visible kind of change of that because, like I say, we can generally change things, but just know the backend actually sets up an entirely new string object and points to that one rather than the old one. Obviously, the old ones will be flushed out the memory anyway once the program ends. So there we go. That's just a little important nuance there. Let's move on and have a look at just some simple operations we can perform with our string array. Now we've set up that proviso. So here we go. In Python, set up a string array of Nick, and we can get to the first character by accessing the 0th element. So notice I've got the variable name followed by the square brackets. That's array syntax, also list syntax in Python, and I want the 0th element. So should expect to see the first letter, which is uppercase M. Okay, so I'm not getting the whole name, not getting my full name there. I would if I had only written the variable name, but in this case I'm only interested in the first character, so I put 0 there. Okay, so that's a simple way to use these subscript operators, square brackets. If we want to get more functions, more methods that we can use, and we'll explore this, we'll explore calling some functions that are bundled up as part of the string class, the str class. Remember, classes have functions, and types are treated as classes in Python: str, bool, int, float. So if we type dir as a function as part of the string class, it's come up in green there, Anaconda color coding, Jupyter, and we can see this is not the exhaustive list, this is actually just a small subset of it. We've got a huge number of different functions that we can call, and we're going to see a few of them. Remember they've got the dunder methods, back to your constructors that used a double underscore init, initialization function. We've got a list of those, and we've also got some other ones which don't have the underscores, but some of them may well route through to call these dunder methods, which is how the Python interpreter works out what to do, dependent upon the context that it's in, whether you are adding, addition, the plus sign, for example, or joining, concatenating. It's the same symbol, it's used in a different context. Okay, adding numbers versus joining data together, concatenating data. So with that, type that into Jupyter. once you're up and running, and then you can explore some of these methods, some of these functions. And here we go, we've got one of them here, find. So there's my string array, my string, and then the name of the array, dot find. Let's call one of those string functions, find me, the element, the position element of this C character. So where is that? Well, it's the third character chronologically, but that should work out to be element 2, because remember we start with 0. So just remember that. If you're new to data structures, you might notice a little bit of error the first time you do it, if you think it's the third character, but actually it's that -1, because you start at 0. It's offset, remember. It doesn't start at number 1. Don't start counting at 1. You start counting at 0. Okay, so just be aware of that. It sounds obvious, doesn't it? But you'd be amazed how that can trick people when they start out, or indeed even seasoned programmers, for just mismatching offsets. Okay, so that's find. So that was lowercase c. Let's show you a capital C. So remember that case sensitivity matters. So there's no capital C. I suppose for some validation, it's generally good practice to normalize the casing of strings so you don't get errors like this. You might want to convert them all to uppercase or lowercase. Remember, there's Python functions to do that. But in this case, there is no capital C, even though semantically there is a letter C in there. It's not capital, it has a different ASCII value. There's 2 different sets. There's ASCII values for the lowercase letters, there's ASCII values for the uppercase letters, so that's why it doesn't find it. And what does it give us in return? It gives us -1. -1 there, meaning that essentially the equivalent of false. We couldn't find it. If we get a positive integer, it must mean the position of the character, letter, symbol, digit, whatever it is we're looking for. But if we get minus value, -1 typically, that means negative. We haven't found it. Okay, so simple binary switch, I suppose you could say there. You could output an appropriate message depending upon what it is that you're trying to find. Okay, so -1, if that was the case, then we could output incorrect. We couldn't find that letter. Okay, so that's reminder. Let's also remind you about iteration. That's going to be essential for navigating through our structures, because we've got multiple values now, all collected in the same variable space, or the alias of that entity. Let's remind you about iteration. Okay? And the for loop is conveniently set up to be able to navigate through these structures. So remember, the syntax in Python is for an alias, in this case x. You could use I or any other value, I suppose, there. You have a variable name in the data structure that we're looking at. So in this case, it's a string in name. So for each letter, essentially is what we're saying there in English, for each letter in name printed out. So x will start at the first character and then work through for each character in this collection printed out. That's then substituted with the character, and we see it on a new line. So remember, print automatically gives us a new line. I suppose if we want it on the same line, we could just do some clever formatting there, but in this case, just to illustrate that it's one at a time, for each element in this name array, print out each character. Okay, so it might not be print, it might be search. We might want to create some manual search to look through every element and only print out the relevant ones we're looking for. We could put a condition in there as well, but this just illustrates just a simple display of the string. Okay, and likewise we do for numbers as well if we needed to, and indeed we'll probably do this for lists and tuples and all the others that we're going to set up. So this one's using the alias I, so for each element, alias of I is going to be replaced for this range. Remember, we start at 1, but we go up to 1 minus that upper bound. It doesn't include it. Okay, so in fact, this is not even a structure. This is just saying, give me all the numbers between this digit 1 and go up until 1 minus this upper bound 4. So that actually prints out 1, 2, 3. If we were in a list, we would probably just say each I in list give us the digits in there, or whatever we store in there. Okay, so we're probably going to be coming back to this for loop. I suppose you could also use while, but for is quite conveniently set up for just that. And indeed, even in traditional languages, we have the longer for syntax, for example, where you declare a variable and basically an alias for int I, and then you start it at a value, typically 0, the start of an array. Int I equals 0, I less than the size or whatever the range is, and then I plus plus. That is set up conveniently to work with zero-based, zero-indexed arrays. Okay, so similarly, for in Python is quite convenient for all the different data structures and types that we want to navigate. Okay, so let's move swiftly on and have a look at lists now in Python. Okay, so you will notice quite a lot of similarities between the traditional array and the list. For example, it uses the square brackets, it's indexed as well. So we've got the subscript operator. Items in a list are treated as elements. There's 0 indexed, it starts at 0. So we could get to an item in the list via the index. We can also use the for loop to print it out. We can also, we don't actually have to declare the size of the list at the start. It's quite flexible. We can add things to it, remove things from it. It's resizable, that's the third point here, unlike static arrays. Remember, we told it exactly how many elements we required at the start. And that has a knock-on effect. Again, if you wanted to explore this further with the data structures and algorithms world, the list is a different approach to an array, even though on the surface it looks similar. Like I say, we're both using the square brackets, but underneath, the list maintains a pointer. It actually is going to maintain a reference to an object in Python, because remember, each type is treated as a class, so we have objects of those classes, rather than the primitive type integers, which you can get in traditional languages. So I won't explore that in too much depth, but underneath it does look different. Just say a little bit more about it as an example. For example, we've got we've got a Python list on the right hand side of my screen, left hand side of your screen, and both use a pair of square brackets. We've got a mixture of types in a list. In Python, we can do that because Python is pretty flexible on lists. We wouldn't be able to do that in a traditional language, a statically typed language. We'd have to declare what type of data we're storing. This could be integers, for example. But here in Python, we don't have to worry about that. We can store a whole mixture of types. And the reason we're able to do that, store a mixture of types, is we have pointers to these locations rather than a fixed size, statically bound array where we've allocated all the memory space up front and we've declared what type of data we're dealing with, which enables us to be able to allocate that memory up front. Okay, so that's a nuance, a difference between a Python list and a traditional array. If you go on to have a look at NumPy arrays are closer to the traditional array, which is good for efficiency, it's good for performance, and good for specifying types going further. So if you want to delve into deeper, maybe explore NumPy arrays in Python. But just getting started, a list should be a good place for us to begin with. Okay, so let's start there, especially as we might be new to this. So this is a Python list. Okay, and in this case, I've decided just to store integer digits, whole numbers. Okay, and L is my alias for my list, and syntax is the assignment operator, as typical, and then a pair of subscript operators, the square brackets, and I have the values within that. So starting at 0, and then incrementing each time, and I've just specified the values all in one go as part of this declaration. Okay, and then I'm going to print them out just by referring to the alias there, L, and there we go. The output probably will include the square brackets. And you notice here I didn't even need to use the for loop to be able to print them all out. I can literally just state the name of the list, If I'm looking for something, I might want to have a for loop to be able to find certain values with a criteria, but to see the list in its entirety, I can just write the name of L, the alias name. Okay. Likewise, whenever we did this with our string array, we can also use the index, the position, to get to a particular place in our list. So here, I'm interested in the 0th element, so I'm going to say, get me the first, chronologically, get me the first item in the list, which should be 1, because that's the first one. Okay, so there we go. That's our first element. 0th element. Just like arrays, they do start at 0. They're 0 indexed. Okay. Random access, so I could type in any value between there to get to one of those items. Okay. We can also get to the end of the list as well. That's a convenient feature in Python. If I had a large list and I didn't know exactly how many elements were added to it, especially if it's a live list constantly being updated all the time. There are items added to it, items removed from it. If I just want to get the last one that was added, I could write -1 to get to the end of that list. And likewise, if I needed to perform other operations, I could also go backwards as well. So I could get to -2, which will give me the second to last element of that item of the list. Okay, so Python quite convenient for that, list management. Furthermore, we can also do what's known as slicing. That's where we basically have a subset of our list. So I might say start at element 2 and go up until 4. So we start at 0, 1, 2, and then go up until, 4, I suppose, would be that. So it's actually 1 minus that, isn't it? So like what we saw earlier, for in range, we're not going to, it's not inclusive of 4, not inclusive of it, it's basically 2 to 1 minus that. So actually getting 0, 1, 2, 3. We're not getting the 4th element, we're getting 3 and 4. So give me up until 4, okay? So useful there for getting a subset of the list, if you want to slice it at a certain place. Okay. As I said, it's a flexible list, so it's not static, it's not fixed like an array would be in a traditional language. In Python, we could just use the functions of it, like we did with the string class. We could type dir to get the full list of functions that come with the list type. Here we can make use of the append function, which appends to the end of the list. I'm trying to think if there's a prepend. There might well be a prepend. That's a typical data structure operation. Prepend adds it to the start of the list. So append adds to the end of the list. So we should see 7 at the end. In this case, I pass 7 into the append function of this list. Should add it to the end. Yeah, there we go. That's good. And likewise, that's inserting to the list. Likewise, we also have the capacity to remove an item from the list. So there we go. I put it into the declaration, so it's there at the start now, and I'm going to call the remove function on the list and remove for this value. So it's actually 0 to 6. So it wouldn't be the 7th index, the 7th element is going to be find the value 7 in this list and remove that at whatever index it's at. Okay. In other languages, maybe in Python too, there's a remove at index where you want to specify the index of an element and remove that one. But in this case, it's going to do it by value. So find the value 7 and remove that whatever index it's at. Okay, and then we go back to the start. And again, just to illustrate to you, you can store the whole collection of different types if you want to. And the reason you're able to do that, of course, is they're treated as classes, and we point to objects of those classes, as opposed to primitive types in other languages, which are not classes, and therefore they're treated differently. Okay, so in some circumstances it's useful, but for efficiency, probably not. So that's a consideration further down the line. It's good and nice and convenient at the start when we're getting started with programming, But later on, when we've mastered the basics, we might want to be a little bit more efficient and optimize. Especially if we've got large collections, we might specify, it might be a bit more code, but it would set things up to run faster, all the different operations that we run on our data structures. Okay, so hopefully that's enough said about lists. As we've seen, they are mutable. We can add things to them, we can remove things from them. Tuples, another data structure, in contrast to lists, are immutable. Okay? They are indexed, that's what I'm saying, so we can get to an individual element randomly if we need to, but they're declared with a different type of brackets. They can touch with the parentheses bracket, aren't they? The curly brackets, as opposed to they're not. We use the square brackets to get to an index, to an element of that tuple, but they're not declared with the square brackets. And indeed, in Python, because we're not using types, the type of square bracket that we use is going to be indicative of the type of structure that we are indicating, essentially. You're going to see in a moment there's not much to distinguish between the types because we're not actually declaring what data type it is. We don't have a dedicated a list type or tuple type. So these types of brackets are going to be important for the interpreter to be able to know what structure it is, and also for us also to learn and know what type of data we're dealing with. Okay, so remember if you see a structure declared with square brackets, that's a list. But if you see it declared with a pair of curly brackets, it's a tuple. And as we said, essentially it is immutable. You can declare it at the start, but you can't add to or remove or change it later. You can still get access to things in it and print them to the screen. There's a few other methods we can look at too, but we can't add or remove from it. It's the constant, as opposed to variable, which changes. Okay, so here we go. Just to illustrate my earlier point, let's just say we're not declaring with the square brackets. If I had declared with square brackets, it's essentially treated as a list. It's mutable, we can change it. Okay, but because I'm declaring with a pair of curly brackets, I won't be able to. Okay, so same digits, same numbers, same values stored there, all comma delimited, and I can still access all the elements in it by using the alias of that tuple. There we go. And you also see on the output it includes those pair of curly brackets rather than the square brackets. Okay, that's a tuple. And as I also said, we can use the square brackets to get to a position of a tuple, just to reference it, to refer to it. So I can still get to the first element of the tuple by using the subscript operator to get to the first element there, which is 1. Okay, but if I attempt to assign a value to it, I'm not going to be able to do it. It's going to tell me off. It says, no, can't do that. It doesn't support item assignment, so I won't be able to do that. I'm only able to declare the values that are going to go into the tuple at the very start. I can't reassign or modify later. I can't even use add or remove or append or any other type of term that's associated with data structures to be able to add things into it later. Okay, so it has a different focus. What I can do though is I can use certain methods like count, so I can count up how many of the same element are in this. There's probably a size element of all, a length element for the total length of the tuple. So I've modified it slightly just to put 3 ones in there. So I can count by value. How many ones do I have, please? Which is 3. Furthermore, I can also get an index of a value. Okay, so if we've got a big tuple, a big long collection of these constant values, I can find out where they are. That might be useful. Okay, so get me the index of value 5, or 0, 1, 2, 3, 4. Yeah, which is 4 there. There we go. So there we go. That's just an example of some of the functions we can use for tuple. But in summary, remember the key distinction is that a tuple is immutable, constant, can't be changed, whereas a list is mutable. We can change it after we've initialized it. Okay. Another key distinction, list is declared with square brackets, otherwise known as a subscript operator, whereas a tuple is declared with a pair of curly brackets, parentheses. Okay, so key distinction there. So let's move on. So those are our first two. I chose those two at the start simply because they're almost polar opposites. Let's move on and have a look at another two data structures. So in the second half now, we're going to have a look at sets, and then we're going to finish up with dictionaries. Okay, so sets. What's that all about? Well, actually, it's a throwback to a mathematical set. So you might be familiar with set theory, if you've done mathematics or computer science before. Set theory, so we can use that for having unique sets of values, like we would in maths. And we indicate this in Python by using another type of brackets. So remember, list is square brackets, tuple is curly brackets, and set in Python is the code braces. I like to call them squiggly brackets. But they're technically the code braces, aren't they? Which in a traditional language we would have as a block of code, a function or a class would be declared with these. We don't in Python, we use the colon, but these are known as the coding braces. Okay, so that's another type of bracket for you to remember. Okay, and just to tell you, they are mutable. You can change them. Okay, so unlike the tuple, they align more with the list. You can change them later. You can reassign values to them. Okay, but another distinction between those data structures we've seen before is that they are inclined to store distinct numbers. That's a unique purpose of them. They can actually, well, I'll make a nuance there, because you can assign duplicate values to a set, but when you come to utilize it, print it out, it's going to resolve those duplicates and print out just one of them, basically giving us a unique set of numbers. The idea is to remove duplicates, essentially. And that's another common function, especially if you've got data entry. A practical real-life use of a set, of course, is that if you've got lots of data entry going on, it might be the case that you have duplicate data being entered. Converting your data structure to a set is a way of removing those duplicates. So you have a set of distinct values. Okay, so let's see this. Okay, so we've got the same values there, but with the coding braces, the code braces there, or the squiggly brackets as I call them, okay, rather than the square brackets or the curly brackets. And I can print out the set, which also mirrors the pair of brackets. Okay, just to illustrate to you, I can add things to it. I've got the add function here, just like we've seen before with the list, and indeed with the tuple. We can still refer to functions with a tuple, we just can't add to them. So with sets, I can add to the end of it, as we see here. Very good, so I can also remove from it as well. So that would get you back to the start, which is very useful. Okay, and let's illustrate duplicates now. So I can actually assign, I've actually got a repeating set here. So I've got a repeating set of numbers, just to prove my point. So notice that I've duplicated 1 through 6 again at the end of that set. And when I come to print it out, I'm only going to see one of those two sets. So there I've resolved all those duplicates, and I'm just seeing the unique numbers there, which is actually quite, it's a very practical data structure, actually, very, very useful in the real world. So there we go, we've got that illustrated as that. And furthermore, you can cast. We've seen casting before. If you enter data in another format, another structure, here a list, let's say, I've got the same duplicate values, just in a different order, duplicated one after another. So I've got pairs of each unique number. If this is a list, we can tell it's got a pair of square brackets, so we know immediately that it's a list. And then I'm going to use the set class name with the parentheses indicating a function. I'm going to cast to a set. Take that list alias L, cast it to a set, store it in S, and again we can distinguish between them because we've got a different pair of brackets. So hopefully this is emphasizing my point that these pairs of brackets are actually essential for us to be able to distinguish between the data structure, because there's no other reference to it. So I suppose we've got an explicit type there. But generally in Python, if you didn't use types, then in theory you could reverse the letters. You could call this S and you could call this L. So the only way to distinguish between them is to use the pair of brackets. Okay, so with that said, let's talk a little about the mathematics here. Let's talk about set theory, because that's another feature of using a set. As in mathematical set theory, as also in Python as well. So let's look at these, just three, there's lots of others as well, but let's have a look at the intersect between two sets, the union of two sets, and the difference between two sets. So I'm going to show you now what you might be familiar with if you've never done set theory is we've essentially got a Venn diagram. Okay, and the intersect is the overlapping portion of the two sets. So let's say this is set A and this is set B. Well, the intersect is the overlap between them, the bit in the middle, where the two values, where the two sets have common values, let's say. And that's indicated in set theory. The notation is this sign here, okay, for that. So you might see things written in the notation that refers to the intersect of the two sets. Of course, you could have more than two sets, but here, just to keep it simple, I've chosen two. So that's the intersect, it's the portion in the middle. The union is actually all of the values. It's everything that's unique to set A, everything that's unique to set B, as well as the common values. I suppose union deriving from unity, or it might be the other way around, unity derives from union, everyone together, unity in the family. Okay, everyone together. So it's everything in the set. Okay, and we've got a different symbol for that, a U here, U for union. And then difference is the other one as well. So we might only be interested in the unique aspects of set A. So we subtract set B from it, essentially. We've got the / sign there, backslash, and we'll see that's the minus sign in Python. Okay, so if we only wanted the unique aspect of set A, not which overlaps with set B, or indeed what's unique to set B, we would say A minus B. And we can also do it the other way around too. So we could do B minus A to get what's unique to set B without any of set A, without the overlap or indeed what's set A. So we see the outline there of set A. All of that is removed and left with the unique aspect of set B. Okay, so in Python, let's have a go at this. Let's translate that mathematical set theory into code. So S1 for set 1 and S2 for set 2. I could have called it A and B, I suppose. But here, set 1A is, I've got 1 through 6, and then set 2 has 4 to 9. So just to point it out to you, 4, 5, 6 are duplicated in both sets. So if I'm interested in the intersect, a symbol in Python would be to use the ampersand, or and in logic. Okay, set 1, S1, ampersand set 2, to give me the intersect. So if I write that in Python, I'm going to get the middle two values, what is common to the two sets, the intersect of those two sets. Okay, for union, unity, remember everyone, all the family, unified, unity, we're going to get the unique but distinct values of the two sets. What you'll see, you won't see 4, 5, 6 duplicated, you'll actually see 1, 2, 3, 4, 5, 6, 7, 8, 9 printed out, and that's using the vertical line, or what we would know as OR in logic. Okay, set 1 or set 2, everything that's in there. Okay, so that's what we're going to see here. We're going to see only one unique copy of 4, 5, 6. We've resolved the duplicates, okay, here, 4, 5, and 6, as well as the unique features of set A and B, set 1 and 2, okay, so you see everything there. And then let's also talk about the difference, so the third of those. We use the minus sign, remember. So if we're interested in just the unique features of set 1, well, we can subtract everything from set 2. So take all of set 2. Is there anything common? Well, there's 4, 5, 6 that's common. Let's take that out of set 1 so that we just get what is unique to set 1. Obviously, 7, 8, 9 are not in set 1, so we're not interested in them anyway. So we're only going to get 1, 2, and 3 with set 1 minus set 2. Same logic, flip it around. If we're only interested in the unique features of set 2, you should be able to infer that we're only going to get 7, 8, 9. 4, 5, 6 is common to set 1, and obviously 1, 2, 3 is not in set 2. So we're just going to get the unique aspects of set 2, which is 7, 8, 9. Okay, so if you wanted to apply some set theory to your Python, you could use these symbols. Okay, so those are some unique features and some very practical features of the sets. Okay, let's finish up with dictionaries, the fourth and final of our basic Python types. And dictionaries have, again, a unique purpose, a very different purpose actually. They operate on a key and value pair. So we would define a key, which we know in our normal world unlocks a door. It is a key to something, isn't it? Open a door to get to a room. It is a key to get to a value. We might know that as an associative array. If you come from background in programming and other languages, an associative array. In Python, it's termed as a dictionary, a key and value pair. But notice here, we've run out of brackets. We've used the square brackets, used the curly brackets, also used the code brackets. So we've got a I suppose we could use the angular brackets, but that's, again, something different. That's typically templates or generics in Java. But notice in Python, the choice, they've gone for the code brackets again. But I suppose we can tell them apart because in dictionary syntax, we use a colon. We do use commas as well to delimitate between key and value pairs, but what sets it apart from the set, it was unintentional, is to use the colon there. So there's no colons in the set, so that is how we can tell them apart. We can tell all the other data structures apart by the type of brackets they use, but we've got two data structures that use the code braces. So we have to look, does it have a colon? If it's got a colon, then it's a dictionary. If it doesn't use a colon, if we've only got commas, it's a set. Okay, so dictionaries, that's an important concept. And of course it does derive from what we would again know as the common dictionary in our natural languages. We use a dictionary, we look up the meaning of a word via the word itself to get the meaning, don't we? So the word acts as the key to locate the meaning. The definition is the word I should use there. Okay, so we use the word to locate the definition. We use the key to get to the value. Okay, so let's take a look at this then. So these are just some arbitrary values, simply the first thing that came to my head. It doesn't mean anything real. But what I have chosen is some continents, some areas of our world, USA, UK and EU. I should have really given them some different values. But in this case, they all have the same value, which is 200. It doesn't mean anything. But what's important to us is the syntax. Okay, so we've got the code braces here, start and end, and then in between we've got a key colon value as a key and value pair, and then comma for another key value pair. That's the vital part here that we need to understand. Okay, so we have 3 keys which match on to 3 values. They've all got the same value in this case. So if I write D there to print them all out, that's what I get. I get the technically I get single quotes from double quotes, but yeah, it's a string. Okay, so that's the unique part of a dictionary, which differentiates it from a set. Okay, so I can also, it's indexed, so I can refer to the positions of the dictionary via the word. Obviously, that's the whole point of this. I suppose I could use positions if I knew them, if it was position 1 or position 2. But more meaningfully, as I was just saying, is that I can use words that refer to the keys, like I would in a real dictionary. I'd look up the definition via the word itself. Okay, the term. Okay, so I can use the term here, UK. Give me what value is associated with UK in these subscript operator, the square brackets. So we've actually seen in all 4 of the data structures that we've looked at, we can get to an index via a value of some kind. This dictionary is the unique one. That's where we can use letters. It's an associative array. In the others, we have to use digits. They're incremented starting at 0. Okay, but we have seen that we can use this index feature for all of them. Okay, which is very useful. We can access midpoints in the midpoint of the list. So yes, we just get the value printed out for this this term, this word, this key. Okay, key of UK. All right. Aha, and here we also illustrate case sensitivity. UK has different set of ASCII values to the uppercase UK, so same semantic meaning, but different ASCII values therefore means we get an error. Confined UK uppercase because they're treated as different. Okay, so just be aware of that. You might want to have a policy, you might want to convert everything to lowercase or to uppercase. It really depends on context. You might want to keep it unedited and filtered, okay? But just be aware of that. It's going to return an error. Okay, I can also add to a dictionary. There might be some functions to do this, but I can also do it via the square brackets as well. So Asia doesn't actually exist in the original list, so I could add it. And the way to do that is to write the key in the square brackets, the subscript operator, and then the assignment operator followed by the value. And then we should see that's been appended, essentially the equivalent of append to the end of the dictionary. So I can do that. And to remove from the dictionary, we've got a slightly different syntax. Because it's a key and value pair, it's not quite as straightforward as what we might have seen before. Because we've got a key and value pair, in order to get to the value, we have to get the key, don't we? So there's 2 scenarios. We could either delete the value, but have the key remaining. Not great, because we've still got the key. We want to get rid of that too. And even worse would be to delete the key before we delete the value, because then we've lost the way to access the value. It's just going to remain in the memory. So what we really want to do is get to the value, delete that, and then also as we work back, delete the key as well. So there's actually a particular keyword to do both of those things, as I was just saying, which is del. Del for delete is a throwback to the C delete command, which again does exactly what I've just been saying. It's usually used for clearing up memory allocated dynamically, like an object or an array, which again you want to be able to delete the value and the key or the pointer. So it's going to handle that for us. So delete first the value associated with that key, and then also delete the key as well, so we don't have that hanging over. Okay, we want to get rid of both of those things, as we see here. So we've gone back to the original list there. Okay, so hopefully that makes sense. Just important to think that one through. As you get memory leaks, you'll get memory hanging over. Okay, and also one other thing to mention is that these, because we've got 2 simultaneous lists, we've got a collection of keys and we've got a collection of values, and they're also stored as separate lists. Okay, so if you actually refer to the keys function on the alias of your dictionary, likewise the values, you can print out the list of the keys and values. How do we know they're lists? Well, pair of brackets, as I've been saying. What type of pair of brackets do we have here? We have the square brackets, which indicates a list. It's not a tuple, it's not a set. Okay, square brackets are the list. Okay, and that gives us those. So that might be quite useful. Useful to know that we've got we're maintaining lists of these aspects separately. Okay, so we might want to only get the list of values, might not be interested in the keys, and vice versa. We might want the keys instead of the values. So there we go. That brings us to the end of this lecture. Let's just summarize. We looked at 4 Pythonic data structures, or types, as they're also known, types of storing data. Importantly, they collect a series of values. They don't just store one value, like a variable. They don't just collect single variables, single values stored in variables like an object does. It's a collection of multiple values. First of all, we looked at the lists. Importantly, they use square brackets, they're comma delimited, and they are mutable. We can change. It's flexible. We can add things to it, we can remove things from it. We then looked at tuples, which are constant. They're immutable. Once we've set it up, we can't change it. And importantly, we tell them apart by using a pair of curly brackets, parentheses. Okay, they're still comma delimited though. Okay, so lists are immutable, and they use square brackets. Tuples are immutable, we can't change them, they use curly brackets. Those are our first 2 that we looked at. And then the second half of the lecture, we have a look at sets and dictionaries. Now, both sets and dictionaries use the code braces, the squiggly brackets, but the sets have comma delimited. There's no colon, whereas the dictionary does have a colon. They're also comma delimited as well. So the key, the clincher, is the colon, isn't it? That's how you can tell them apart. That's where you have a key and value pair. As we just said, it's useful because we can use more meaningful indexes, such as terms and words for things, rather than just random digits, which don't necessarily have a value. That is always meaningful. So we can have a unique key to get to a value there. And with sets, of course, we remove the duplicates. We don't print them, I should say. We don't print duplicates, and we can also apply set theory for mathematics on them. Okay, so hopefully that's enough to give you for now. Hopefully that's enough to be getting started with. I think now you probably need to jump into the exercises and apply some of those basic operations on these different data structures. So I'll let you do that, and I'll catch you in the next lecture.